Okay, just a quick video on terminal velocity. And this is transitioning from our discussions of forces and an idea that's called equilibrium. It's something that we haven't expressly given a name to except maybe in your reading. But the last example we did, which we had the sign suspended from a couple of lengths of chain, that is an example of an object that's in static equilibrium. And the idea of dynamic equilibrium is also something we can look at. Okay? And equilibrium itself, at least at this point, we'll start talking about it again when we start talking about torque. But at this point, the condition for equilibrium is that the net force on the object is equal to zero. And if you have that, well, then all of the forces on that object must sum to zero, which means via the second law that if all this has to equal zero, that implies, of course, that the acceleration of the object is zero. It does not imply, okay, that acceleration, or rather, velocity is zero. No, right? It could be, right? The sign, so-called static equilibrium case, is a place where you have net force is equal to zero, you have acceleration is equal to zero, and v equals zero. But that's a special case. We know that when you have an acceleration equal to zero, that just tells you that you have a constant velocity, right? Not necessarily one that is zero. So when something is falling at terminal velocity, that is another example of an object moving at a constant velocity, albeit it is moving, and so we give it the name or the descriptor dynamic equilibrium. All right. So if you have a situation where you have a falling man here, and he's got maybe a little guide parachute on him or something like that, and he's just started his fall, right? So maybe just got out of the airplane, immediately pulled this little parachute, and you're going to have two different forces acting on him. Okay. Previously, we would have said, oh, well, there's only one force acting on him because we haven't really considered drag. But when you're talking about something that's moving quite quickly, or something that is quite large, so has a cross section that's large, like you would if you had a little parachute here. Okay. We need to start considering the idea that drag from the air would be acting on that thing. And if we ever consider objects moving through fluids other than air, so water or, I don't know, many more viscous and more dense things, then we definitely need to be considering the drag acting on those things if we're going to have an accurate picture of what's going on with those objects and their motion. So when this person just drops out and pulls their parachute, okay, so just getting started. In other words, the velocity of this person is relatively low. Well, then the force of gravity is quite a bit larger than the upward force of drag, which is going to oppose that downward force. Okay, they oppose the direction of motion, and since this person is just falling straight down, force due to drag acts straight up. And if the velocity is relatively low, well, then the force due to drag is also relatively low. But that means that the net force in this situation, and I'm not going to add it to the free body diagram as another arrow because remember we only ever enumerate the various different forces acting on a person, and then it's the sum of those that gives us the sum of the forces. Okay, but the net force in this direction is down, and that means that the acceleration of this person is down, right? We know that something's going to fall faster and faster and faster until it hits its terminal velocity. So what does that look like? Well, what that looks like is that if you play the tape forward, if you take this person falling for some time, and the velocity of this person grows and grows and grows, well, then the drag from the air colliding with them and moving across their surface is going to get bigger and bigger and bigger, okay? Drag, as it turns out, is proportional to velocity, and strictly, in this case, it would be proportional to velocity squared, okay? But as velocity grows, the drag force gets bigger, and you'll eventually get into a situation where the upward force of drag is going to be exactly equal to the force of gravity downwards. Now, if you think about that, well, that means that the net force on this guy is 0. That means that the acceleration of this guy is 0, and so his velocity must now be a constant value. This is why you can't exceed your terminal velocity. That's so you get up to that point and then you stop accelerating unless you somehow change, how you're moving through the air. Like if you got rid of the parachute, right, his drag would go down because there's less stuff attached to him running into the air as he drops, okay? But all other things being equal, you cannot exceed this velocity because, kind of by definition, your acceleration is 0, so you can't be changing your velocity. And the reason it's 0 is because these two forces, the upward drag force and the gravity downwards, are balancing each other out, giving a net force of 0. So the condition for terminal speed or terminal velocity is this, okay? And that means that mg, the product of the mass of the object, times our 9.8 meters per second squared, has to be exactly equal to the magnitude of the drag force. Next time, in the next little video, I'll take a look at what equations govern the size of this drag force. We've already discussed how it is proportional to velocity, so the faster you're moving through a fluid, whether it's air or water or whatever, the larger the drag force is going to be on you. But there are some other parameters that matter, and we're going to take a look at those then. So I'll see you for that one shortly.